differential equations, which we have already seen differential equations. We just didn't call them that necessarily. But basically, we use them everywhere. In biology, social science, they're all over the place, these differential equations. Anytime we want to work with rates of change, we use differential equations. There's an example of one. Now, you might not be used to seeing it written in that format, but that actually is Newton's second law of motion. Force equals mass times acceleration. Well, acceleration, I've just written it as the second derivative of displacement with respect to time, is equal to some function of x, which happens to be the force. But that is a differential equation. This one here, possibly you don't recognise, but that one is an equation that controls damped oscillation. And damped oscillation is like a shock absorber, where it goes up and down, but then it gets dampened and gets smaller and smaller as you go along. That would be an equation that describes that. This one here is known as the Lotka-Volterra equation, the predator-prey equation, talking about how populations are happening over time. These are all just differential equations that involve a derivative. Now, the order of the differential equation is basically the highest order of the derivative. So the first one would be a second order differential equation. So with the second one, whereas the last one there is just a first order differential equation. So whatever the highest derivative is in the equation, that's the order of the differential equation. So how do we solve these things? Basically is integration. That's how we solve differential equations. Now, we have a thing called a general solution of a differential equation, and you get a family of curves. Pretty much it's the same as what we call the indefinite integral. So we've got plus a constant. You can get a whole series of different curves depending on what the constant is. And then we have a particular solution that solves an initial value problem. Well, that's like our definite integral. We're given some initial conditions that we substitute in, and then we can pinpoint which of the particular curves in the family of curves we're interested in. That becomes the particular solution. Something like this. It's a differential equation. I could do it like so. If I just have everything that involves x on one side of the equation, everything that involves y on the other side of the equation, and how do we solve them? Well, we use integration. I can set up my equation like so. And then on either side, I can integrate those. They both turn out to be log functions. Then playing around with the log laws and things like that, I end up with y is equal to some constant over x would be a solution to this particular differential equation. So here is the general solution. You get a whole family of curves, all these hyperbolas, different hyperbolas depending on what c is. Now the one I've put there in bold would be a particular solution if my initial condition was that when x equals 1, y equals 1. That would solve that one. That becomes the particular solution, y equals 1 on x. Linear differential equations, that's what we're interested in. Now linear means this. We know equations of the line, the highest power of the unknown is 1. Well, with a linear differential equation, the highest power, not order, the highest power of the derivative is 1. So all of these derivatives, the y dx, dn minus 1y dx, they're all to the power of 1. That becomes a linear differential equation. The coefficients, it doesn't matter. I mean, they could be any functions you like. And then we come to these things, just simply first order linear differential equations. So the highest derivative will be the y dx, the first order. And then it could be plus some function times y and equal to some function as well. Now if function x equals 0, we just basically go and find whatever the indefinite integral is. If it does not equal 0, we end up multiplying the whole thing by what's called an integrating factor. And that factor turns out to be e to the power of the integral of whatever the coefficient of y is. That's what's called an integrating factor. So here's the equation that I wish to solve. I will work out my integrating factor. Well, the integral of the coefficient of y. The coefficient of y is 4 on x. Integrate that, I get 4 log x. Rearranging that around, I get that u is equal to x to the power of 4. So I'm going to multiply everything by x to the power of 4. Remember, it was e to the power of that integral. So e to the power of log x to the power of 4 is x to the power of 4. Multiply everything. Now why do that? Why does this work? Because if you look at that closely, what you have just done is you've created the product rule. Write down the first, diff the second, plus write down the second, diff the first. Okay? See, the derivative of x to the power of 4y would be x to the power of 4 times dy dx plus y times 4x cubed. You have created that situation. So therefore, the left-hand side I could now rewrite as the derivative of x to the power of 4y. Oh well, now I can just integrate. X to the power of 4y must be 3 times the integral of x to the power of 6. Add 1 to the power over the power. There is an answer. I mean, that works. Mind you, we tend to write these things as y equals. I can very easily make y the subject of that. Divide everything by x to the power of 4. I suppose the big difference is we used to see an answer with just plus a constant. Well, this one doesn't. It's a constant over x to the power of 4. It doesn't have a constant number at the end of it. We're going to verify that this derivative is in fact a first order linear differential equation, so it satisfies those requirements. Well, dy dx is certainly to the power of 1. It does that. But let's play around with it. So y plus x on x I could simply rewrite as y on x plus 1. If I move that y on x to the other side, there it is. We have dy dx times, well in this case 1, and then I have y times minus 1 on x, so it's got a function times y, equals, well my function on the right hand side is just the number 1. So yeah, that is a first order linear differential equation. Find the general solution then. Dy dx minus y on x is equal to 1. My integrating factor, well, whatever the coefficient of y is, so that's integral of minus 1 on x, which is minus log x. I want to multiply everything by e to the power of that. So playing around with that, well, that's 1 on x. I'll multiply everything by 1 on x. I have set up the product rule. d dx of y on x equals 1 on x. Now notice this now that we've done 2 of them. Finding out what this function is very easy, because it's simply the integration factor times y. So we end up with y on x equals log of the absolute value of x plus a constant. If I make it y equals the subject, I'll get y equals x log x plus some constant times x, would solve this differential equation. Try this one. Y dash plus 3y is equal to x. Let's work out the integrating factor. Okay, in this case it's just e to the power of 3x. Multiply everything by e to the power of 3x. That means the left-hand side is y times the integrating, so e to the 3x equals x e to the 3x. Of course, you can't do that really in extension 1, but we could use integration by parts, we've seen that, to go and integrate x e to the 3x. U equals that, sub it in, and we have it. Integral of e to the 3x, whew, eventually there's our answer. Y is x on 3 minus a ninth plus c e to the minus 3x. 2022. They want us to find the particular solution to this differential equation, and it's a particular one because they've given us an initial condition that it passes through the point 0, 1. So x minus 2 dy dx is equal to xy. I want to get it to a point where everything that involves x is on one side, everything that involves y is on the other side. I can very easily do that with this one by dividing by x minus 2 and then also dividing by the y as well, and we've got it. The limits, we've got to match the limits. They told me that when x equals 0, y is equal to 1. We want to find a relationship between x and y. Playing around with the right hand side, it's going to be easier to make that x on x minus 2 1 plus 2 on x minus 2. Now I can integrate both sides. On the left hand side I get log y, right hand side x plus 2 log x minus 2. Substitute in. Now you'll notice the x changed to be the log of e to the power of x. So I want to play with my log laws to bring these things together. That now means the log of y is the log of x minus 2 squared e to the x on 4. Therefore the absolute value, because it was the log of absolute value, of y is equal to that. So y is plus or minus. But remember, we are looking for the particular solution that solved the problem that went through 0, 1. So the question is, which one is it? Well, we want the positive. The positive would make that 0, 1. If I went for the negative, I'd get 0, negative 1. So that's not the one we want. We want 0, 1. So there's our solution. 13a, we'll start looking at these differential equations.